Okay, let me continue to discuss with you the next part of the course. Yeah, so now this is another example. It's not really example, but similar to example, showing you the, how can I say, the prediction of transversal tensile strengths based on the mechanics of material approach, not based on the strength of materials. And we still consider the unidirectional lamina. And we assume that we have the perfect bonding between the fiber and the matrix. We also assume that we have uniform spacing of fibers. The fibers and the matrix follows the Hooke law. Yeah, and there's no residual stress. So, in fact, we do not have perfect bonding between the fiber and matrix because the interface is quite complex, and there's always exist the defects there. Different kind of defects. Yeah. It's quite difficult in order to have a uniform spacing of fibers. It depends how to, how can I say, you create the prepreg, the resin transfer molding process, and how we can guarantee the uniform spacing between fibers. Oh, it's quite difficult. The fibers and matrix follow the Hooke law. Yeah, can be. And there is no residual stress. Yeah, during the fabrication of the composite. Yes, we also have some kind of factor like the heat. The thermal gradient can cause the residual stress. If we lay off the plies in asymmetrically, which means that the upper layers and the below layers are not symmetrically, and therefore, yeah, you can have some kind of material rough or the distortion, and this created by the residual stress. So the assumption, the three among four assumption here, yes, it's just for simplify the problem to solve. But in fact, in reality, there's no, we do not observe these, how can I say, for example, perfect bonding between fiber and matrix, uniform spacing, and no residual stress. In fact, it's impossible to have this. Uh, the transversal deformation of composite is calculated as follows. So we have the deformation of the composite equal to the sum of the deformation of the fiber and that of the matrix. And then you have this, yeah, for example, yes, the strain of the composite. Yeah, is equal to, yes, I just want to mention about the final equations because just to save time. We do not want to go into detail. Yeah, just to show about the result for this situation. And therefore the sigma 2, yes, tensile or transversal tensile strength ultimate equal to the E2 multiplied by the epsilon 2 T ultimate. Yes. And what about D and S here? You can see on the right side of this slide where you have, for example, S at the distance between the center fiber here, and D we have the diameter of the fibers, and therefore you can put it into this equation and you have the final, how can I say, relations in order to calculate, to predict the transversal tensile strength. But it's quite important to assume this one, the two assumptions, in order to have the final expressions. So for example, there are some that stress in the fiber equals to that in the matrix. Yes, quite important. And assume that the transversal failure is due to the matrix. If not, yeah, the mathematical expression will be different. Yeah, but just be careful. And we also have another equation in order to show the predictions of transverse compressive strength. Uh, the previous slide show you how to calculate or to predict the transverse tensile strength, and here show you how can I say the prediction of transverse compressive strength, where we have the sigma 2 composite equal to the E2 epsilon 2 composite, where we have uh, the strength is equal to the D diameter of the fiber divided by the S is the distance between the two center of the fibers multiplied by the elastic modulus of the fiber of the matrix divided by the elastic modulus of the fiber plus 1 minus D divided by S multiplied by the epsilon of the matrix. Yes, just the definition, ultimate compressive failure strength of the matrix. Another predictions rely on the in-plane shear strength. Yes, still rely on the mechanics of material approach. And we assume that we apply a shear stress tau 1, 2, which result in shear deformations. And the shear deformation can be calculated as follows. We have delta C equal to delta F plus delta M. And we have this is somehow regarding the hook law. And then we have to find an expression. Yeah. Oh, come on. The prediction of the in-plane shear strength under the shear stress loading, and we assume the shear stress in the matrix equal to the shear stress in the fiber. And then we have the shear strain relations based on the below equation here. And then we have the gamma 1, 2 composite equals to the D divided by S multiplied by the ratio of GM divided by GF plus 1 minus D divided by S. This multiplied by the gamma 1, 2 of the matrix. And then we also need to apply the assumption that the shear failure is due to the failure of the matrix. And then we have the expression of the gamma 1, 2 ultimate equal to blah, blah, blah. And then you substitute tau 1, 2 equal to the G 1, 2 multiplied by the gamma 1, 2. And then you put the available information into the gamma 1, 2 ultimate. And then you have the final expression in order to calculate the in-plane shear strength. Yeah, this here. Yeah. And apart from these mechanical properties, thermal properties can also be calculated by the use of rules of mixture. For example, the coefficient of thermal expansion. Yes, we know about the definition. It's defined as a change in linear dimensions of a body unit length per unit length per unit change of temperatures. And for the unidirectional lamina, the dimensional change differ into direction 1, 2 for sure, because the type of material, I mean composite, behave anisotropically. And therefore, there's no doubt that the dimension will change differently in different directions, 1 and 2. 1 is, let's say, longitudinal direction, and 2 is the transversal directions. And If we call alpha 1 and alpha 2 are the linear coefficients of thermal expansion in the direction 1 and 2, and final expression of 1, 2, final expression to calculate the alpha 1 and 2 based on the thermoelastic extremum principle is, yes, alpha 1 equal to 1 divided by E1, the thermal expansion coefficient of the fiber, EF VF plus alpha M EM VM. And for the alpha 2 thermal expansion coefficient following the transversal directions, so we have 1 plus VF alpha F VF plus 1 plus Vm alpha M Vm minus alpha 1 Mi 1 2. Mi 1 2 here is the Poisson ratio. And we can predict, yeah, the longitudinal thermal expansion coefficient alpha 1. So this can be done based on the knowledge of mechanics of materials. The expansion of the unidirectional laminar in the longitudinal directions, the temperature change. So we have F1 is equal to the sigma 1 multiplied by the area of the composite. So over the load is F1 is 0, yes, because we just assume that the strain is due to the thermal factors, not caused by the external force, but caused by the thermal factors. So 0 is equal to sigma FAF plus sigma MAM. Yeah. And stress caused by thermal expansion mismatch between the fiber and matrix, because different material will have different thermal expansion coefficients, and the thermal expansion mismatch will cause stress between two different components of the composite. And we have sigma F equal to the EF multiplied by the epsilon F minus alpha F delta T. Yes, due to the change in the temperatures. And similarly, we can calculate the sigma M, or the expression to calculate the sigma M. And we assume that the strain for the fiber equal to the strain of the matrix and equal to the strain of the composite in the longitudinal directions, and therefore the strain of the fiber equal to alpha F epsilon FVF plus alpha M EMVM divided by the sum of EFVF plus EMVM, and these multiplied by the delta T. And if we let the material expand freely in longitudinal direction 1, and we have the longitudinal strength epsilon 1 equal to the alpha 1 multiplied by the delta T. Yeah. And since we assume that the strain in fiber equals to that in composite, meaning that the epsilon composite in the direction 1 or in the longitudinal directions equal to the strain of the fiber, and then blah blah blah, we have alpha 1 in the green dash rectangular equal to the alpha FEF divided by E1, and these multiplied by the volume fraction of the fiber, plus alpha matrix, thermal expansion coefficient of the matrix, the Young modulus of the matrix divided by the E1, yes, the Young modulus of the composite along the longitudinal directions multiplied by the volume fraction of the matrix. Yeah. Yes, so where is it? I think 66. Yeah, we can complete the chapter 5 when we finish the slide 66. And as I already discussed with you, uh, the final part of the chapter is for you to read at home. Yeah, regarding the macro mechanics of composite. Yeah, yeah. Just to show you how to predict the mechanical properties or even the thermal properties of the composite, which composed of different constituents. Yeah, but the predictions is in general difficult, especially if you consider the case which is different from the unidirectional lamina. And if you plan to solve the problem in the abacus, for example, on this, so you see how different the process is. But generally speaking, yeah, just provide some kind of input, the regime, mesh, boundary conditions, constraint, so on. Yeah, but keep in mind that you need to know about the phenomenon, the process itself, so that once you have the simulated results, you can analyze and to be sure that the the result is reliable, not not just for seeing for fun. And we can also predict the coefficient of moisture expansion. So the composite can be expanded under the influence of the moisture or water absorption. So polymetric composite can absorb water, expand, and therefore we have the change in the dimensions. That is the unexpected situation. Yeah, for sure. Coefficient of the moisture expansion equal to the change in the linear dimension of the body per unit length per unit change in width of the moisture per unit width of the body. Yeah. And we have two coefficients, B1, beta 1, beta 2. And we have the linear coefficient of moisture expansion in direction of 1 or 2, which means the longitudinal and transversal directions. Yeah, I do not want to read on the symbols here, just to show you we have the slide about the mathematical expression of the equation to calculate the B1 and beta 1 and beta 2 together with uh, the definition of these symbols or providing you the nomenclatures. And in most polymeric matrix composites, fibers do not absorb moisture, and therefore the delta Cf equals to 0, because delta Cf here is the moisture concentration in the fiber. No absorption, delta Cf equals to 0, and therefore you will have the brief form to the equation to calculate beta 1 and beta 2. And in the case that with high ratio between the young modulus of the fiber and that of the matrix, the fibers do not absorb water as we have discussed or assumed before, we can simplify the equation to calculate beta 1 and beta 2. Beta 1 is 0 and beta 2 is 1 plus the nu m multiplied by the ratio between the rho c divided by rho m and the beta m, where the beta m is the coefficient of moisture expansion of the matrix. And last but not least, the overall load in the composite F equal to 0, because we have expansion is not due to the application of the external force, but due to the absorption of the water. So the expansion is not due to the presence of force F1, and therefore the force F1 is zero, meaning that sigma 1 multiplied by the area of the composite equals to 0 and equals to sigma FAF plus sigma MAM. We have the more simplified or more simpler, or the simpler, sorry, simpler, yeah, uh, from the equation when the force is 0. Yes, and we have the stress in fiber together with the matrix, the stress in fiber and the matrix caused by the moistures. Yeah, the mismatch between the expansion between the fibers and the matrix, yeah, cause the stress. And we have the stress of the fiber, the stress of the matrix are calculated based on the three equations listed here. And if we assume that the strain in the fiber equals to the strain in the matrix, epsilon F equal to this epsilon M. Yes. Yeah, a lot of assumption in order to find out. Yeah. And okay, we can come to the final expressions. Just the final image just to show you the final expressions of the beta 1. Okay. And for the others, macromechanical analysis of the laminate. Yeah, it's for you to read at home. Because just try to read, yeah. Because you will have different stress and strain components when you consider the representative volume elements. And instead of writing the hook law by separate equation, and you put into the matrix form, yeah, for consideration. Yeah, and we have tensor. Yeah. So, but okay, just a preparation for you to read, and hopefully you enjoy it. Okay, now let me turn to the final part of this course, the chapter 6, where we focus on the corrosions. So the corrosion can happen with different materials, and for those metals, especially like steel, is very sensitive to corrosion, especially under the influence of the corrosive environment, and except for the stainless steel, and metals is account for, let's say, a considerable amount of part inside an airplane, and therefore is had a certain meaning when you consider the the corrosion in the metals within an airplane. In order to know about the phenomenon of the corrosion and to find the solution in order to protect the metal part of an airplane. Yeah, for sure, it's very important. Because when the material is corrode,
Thầy
and then
ơi,
you,
hình
yes,
như mà thầy chưa share slide á thầy.
no, 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 I have not yet shared. I
À,
have,
ok.
I have. Yeah, yeah, just some information about the corrosion of the chapter 6, but now I'm in Sam. Yeah, okay. Yes. So as similar to the case that you have present in front of a lot of audience, when you defend your thesis, for example. So initially, you should present an overview of what you have done, what you have dealt with before you show the specific content of the slides. So it's kind of guide your audience to the specific content. Yeah. So this is kind of an approach. Yeah. Yeah. So giống như các bạn khi mà trình bày vào một cái nội dung nào đó, khi các bạn trình bày đồ án tốt nghiệp chẳng hạn, thì khi mà chúng ta bắt đầu chúng ta không thể nào chúng ta đi trực tiếp vào cái slide trong cái thế từ chúng ta bắn. Một trong những cái mà nó tự nhiên hơn là các bạn bắt đầu nó vào một cái câu chuyện nào đó trên thực tế chẳng hạn. Ví dụ cái máy bay bao nhiêu trường hợp nó xảy ra cái hiện tượng là ăn mòn, đúng không? Ăn mòn đấy thì đem lại những cái tác hại như thế nào, và vì những cái tác hại đấy cho nên người ta phải tìm hiểu về ăn mòn, người ta phải đưa ra các cái biện pháp để khắc phục cái sự ăn mòn cho các cái chi tiết làm bằng kim loại trên máy bay chẳng hạn. Thì với quan điểm như vậy thì chúng ta sẽ tiến hành nghiên cứu nội dung của chương số 6, chương cuối cùng là về ăn mòn cho vật liệu kim loại trên máy bay. Đó, dạng dạng như thế. Thì đấy là cách mà tôi bắt đầu cái chương số 6 thôi, nhưng còn tôi cũng chưa đi vào nội dung. Vâng. Okay. Corrosion. So actually, I have mentioned that we have different kinds of materials actually, and there are considerable amounts of materials that can be corroded under the influence of corrosive environment. But materials like metals, so some of metals so very sensitivities to the corrosive environment and can be easily corrode under this environment. And that's the reason we pay attention, or we study the corrosion of the aerospace metals, because metals, many metals are very sensitive to corrosion. On the other hand, composites are quite stable. When you consider the corrosion, or is stable under the influence of the corrosive environment. There's no problem. Especially the polymeric based composite. Yeah. Oh, okay. I have heard the sound tick, so I think of the fact that somebody asked me for the permission in order to join the class, but no. Yeah. So the corrosion of metal in aircraft can be observed in the aircraft structures or aircraft engines. This is an expensive problem, and it's cost over 2.2 billion US dollar over a year. And this is the common cause among different factors that lead to the damage of the parts, which is account for 25% of the damage. And the other could be under the influence of the load, heavy load, for example, or under, what can I say, other factors. Yeah, who knows? The definition of the corrosion, this is actually the chemical attack of the metal, which lead to the deterioration and loss of the materials. So, for example, we have the moisture condense. Moisture condense. This means that we have the water. We have the water on the metal surface, something like this. Ngưng tụ hơi nước. Moisture condense on metal surface. Seep into and drift down the surface, so something like diffuse to the matter under the surface of the fuselage. Lavatory, yeah, lavatory. We wash our hand. Yeah, many activity inside the laboratories, and which can cause the moisture absorption to the surface of the materials. Nicali, which lead to the corrosion. And that's the reason we should maintain the humidity being smaller than 5 to 8% in order to minimize the condensation of the water. And therefore we can minimize the water absorption onto the surface of natures, for sure. Common example of corrosion damage to the aircraft, to an aircraft. Sorry. For example, corrosion thinning of fastened joints in water intrusion. Intrusion, sự xâm nhập của nước. Fastened joint thì nó giống như là những cái liên kết sử dụng bu lông đai ốc hoặc là liên kết sử dụng đinh tán. Nhưng mà tôi nghĩ là thường nó liên quan đến bu lông đai ốc, bởi vì chúng ta siết là siết giữa bu lông và đai ốc, cho nên người ta gọi là fastened joint. Pitting of exterior skin, pitting, which is create a hole on the surface of the part, which is the area of stress concentration. First, crack can easily occur there, or now the intrusion of the water can penetrate to the area, to penetrate deeper to the solid materials. Yeah, to solid materials. Stress corrosion cracking is the corrosion caused by the corrosive environment and the tensile stress. So please keep in mind that we have the two stress stages. The first stress stages is the compressive residual stress. So this is the good case. This is the good case, because if there is crack on the surface of the materials, and the compressive residual stress tend to close the crack and therefore enhance the fatigue life. And that's the reason after many manufacturing process, we will use the process of shot peening, for example, applying the autofretage pressure for the pressure vessel, applying the sandblasting, for example, in order to implement the residual compressive stress to enhance the fatigue life of the component. However, on the contrary, if you have the tensile residual stress, so if you already have the existed crack on the surface, and the tensile residual stress tend to open the crack and promote the crack propagation to the solid materials, and therefore in general the tensile residual stress is detrimental or is negative to the fatigue life of the materials. And basically the stress corrosion cracking, this means the corrosion occur under the influence of the external of the stress and the humidity, and is occur at the region where you have the drill holes or the cut outs, or you may have the corrosion of the fuel tanks. It's not under the influence of the stress, but also under the influence of the fuel itself. Fuel itself. There are several factors that can be used to determine the type of corrosion and the speed of corrosion. For example, the compositions, uh, the metallurgical properties, the heat treatment process, the surface film and protective system. So for sure, if you paint outside the part to prevent the direct contact of the moisture and the part, and therefore it can protect the part from corrosion to a certain extent until the coating is damaged, and then we have problem. The stress, voice, or other defects. Composition, concentration of a corrosive liquid or gas. And last but not least, we have the influence of the temperatures and the moisture or the humidities or the woods, the gas, whatever you call it. And on the right side, you will have the survey example of the surface corrosions, which look terrible. Corrosion cracking. So we have the crack on the surface, which is induced by corrosion. You have the exfoliation corrosion. Nó dạng như ăn mòn và nó tách cái lớp bề mặt ra thì người ta gọi là exfoliation corrosion. And these are the three among many examples regarding the corrosion damage to the major aircraft components. Come on. And there's some, how can I say, the two graphs show you the reason, good in general, the reason in general which cause the corrosion. Yeah. Or we can say the common source of corrosion during the design and during the manufacturing stage. And the other is the reasons cause the corrosion during the in-service operation of the aircraft. And as service engineers, for example, you need to pay attention because during the maintenance phase, you will need to, how can I say, appropriately handle the process, handle the part, following the process set by the manuals in order to guarantee that the process is handled correctly to avoid any, how can I say, factor that negatively influence the quality of the part after the assembly process. So for example, in the NASA center, so when they example the equipment, the satellite, for example, and they did everything inside the clean room. Similarly, in the case of fabricating the Intel chipset, for example, just to protect the system from the dust, for example, moisture, or in other words, inside a controlled environment. Controlled environment. But here in Vietnam, we have the controlled environment in order to maintain appropriately different components of an airplane. Yeah, this is the question for you, and therefore you need to pay attention to these factors so that we try to eliminate or reduce the negative factor that can affect the uh, the normal working condition of the aircraft and to avoid the risk of corrosion. Avoid the risk of corrosion. For example, during the design and manufacturing state of an aircraft, during design, we can design the aircraft with poor drainage. Okay, poor drainage. So with the toileters having poor drainage, yeah, we have a big problem inside a home or an apartment. Needless to say, inside an aircraft, inside a laboratory, crevice, hair, stress, using dissimilar materials because it's caused different in electric potential, yeah, material selection, yeah, and during the aircraft manufacturing process, some source of corrosion can be the poor material finishing, so very rough surface, yeah, without the application of the painting process. poor bonding process, for example, applying incorrect heat treatment, forget to perform the annealing process to relieve the residual stress, for example, and so on. A lack of anodizing material just means that we perform the anodizing process in order to protect the materials, or using the sacrificing anode. Is another examples in order to protect the material from corrosion. Operational aircraft. There are several sources of corrosion during the in-service operation. During the maintenance problem area, so for example, the neglect, yeah, neglect something, or for example, neglect to follow the process suggested by the manual instructor, manual instructions, or sorry, improper repair can be also the source that lead to the corrosion of different components inside an aircraft.